Well, we begin the discussion again. I mean, this we are starting with this. We have discussing the groundwater flow. Then this the flow velocity is the thing that that we will discuss now. Flow velocity. Flow velocity. Having to see in the flow velocity part, let me explain few things about here. What is generally, if you can see that generally a very popular notion that Q is equal to A into V, that A is the area of the cross section, V is the velocity, that so also V is equal to Q divided by A. Here in this Darcy's case, if you Q divided by A is, as we have done for this, versus this K dH by dl that we have done for Q. If we this the K cancels out, K dH by dl, that is this very simply can be written like this, velocity as this. So this velocity is known as the Darcy velocity. Darcy velocity, this requires a certain explanation here. Darcy velocity, this Darcy velocity, if this can be, this is known as the Darcy velocity. Now let me explain this Darcy velocity here. Suppose in this case, so here say in case of a Darcy velocity, what is generally understood is this. This is, if this is the cross section of the aquifer under consideration, it talks about that their cross section, there will be some impervious zones, some pervious zones like this. Say here, not coming in there, coming now, it's coming. Okay, so here you can see this is the impervious section. If you just make a section in the aquifer, this is a section, the section of the aquifer. These are the impervious zones, impervious sections or impervious zones, you can write, or sections. Here this is the area, the white portion is the void. This is the void. When you are considering this Darcy's, particularly this here, considering here like this, what we are trying to say here is this area is the water is flowing through this whole area. Water is flowing through the whole area, irrespective of the impervious zones, So the velocity that we are measuring here is, so Darcy velocity, you can see this, this Darcy velocity here, Darcy velocity, this is deals with the complete cross section. Darcy velocity is basically deals with the complete cross section, but actually the flow is taking place. But if you just try to observe here in the same cross section again, if we just try to redraw this, so here the actual flow is essentially taking place here. Through the void. through the void. So you can see this flow remaining same, the velocity actually is higher. Flow remaining same, since the cross section is decreased, so the velocity will be higher. So this is where, this is what you generally say, as to say this is the actual velocity. You know, this is the say the actual cross section through which water is flowing. All right. So Darcy velocity deals with the complete cross section here, in a complete section, or but the actual cross section through which the water is flowing is basically the voids. We are not including this impervious layers. As a result of this, you know, this is what, if you can observe it, this one is as we see this, you know, this is known as the Darcy velocity. So as in actual the water is flowing through the voids, the area of flow decreasing, the velocity increases, and it increases by a factor of the inverse of porosity, which is nothing but, you know, you can very well identify this, is this, you know, as you know, this Q would be V into A here, this one is V into A, also there is V dashed into A dashed, or this V dashed is equal to V divided by A dashed by A, A dashed by A, yeah, A dashed by A. So you can see here, this one is nothing but, you know, what we have found out, what we have said, if you are just A into, if you just multiply by the volume factor, the width factor, or the depth factor here, the depth factor cancelling. So the volume, we have said the void in case of void. So, you know, if you are multiplying by the width, area multiplied by the width, that gives the volume, the width cancelling out. So you can just generally find out. So here itself we can write it like this, say W, this W, the W without change is this, into W, this one is nothing but the porous volume divided by the actual volume, and this is known as porosity. That is what we generally try to know. So here you can see this, as this one is as not necessary to be emphasized, but nonetheless let me tell you that this one is V dash would be always more than V, because of eta is less than 1. Eta is less than 1. So, you know, you can find out, so we can very well find out here, we can replacing these values of V by V dashed, we can find out this, you know, this one can be, say we can find out this K into dH by dL divided by eta. So here, so this is the actual velocity. So you can find out this one is and actual velocity. So we are just making a notation here. This v dash is equal to actual velocity. Actual velocity, right? Now let me just give you an example, small example here, how actually it can be physically be used. This thing can be physically used and where it would be of great importance. Particularly great importance, is many cases is like this. Say there is a mine source like this. If it is say mine, this is say a small block of mine. Here the water is, as you know, the water collects in the sump. This is where the sump is. Very simple diagram. Okay, you have a water regime like this. You have a water regime going like this. This is the structure. So you can find out. These are the rocks. Essentially the rock structure. This is what is a rock structure. So you can find out, say different kinds of rock structure taking place like this. So it just generally that a different kind of rock structure, and we have one aquifer cutting across this area. What happens here is, now due to the surface mining, due to the mining activity and things like that, we can expect there is a crack being developed, and which is naturally takes place. Is very common. I mean, is nothing to be very nothing to be nothing to dispute here. So here you can see the contaminant is essentially reaching here, and we consider that this contaminant is essentially dispersed into the cross section of the groundwater regime almost immediately and almost in the same concentration in all the places. We consider this. Now here, having said this, so this is what is, suppose what is here is, say we have one installation here, wherever it is, say here we can see this a groundwater pumping at a distance, you have a groundwater pumping installation. We have a pumping installation which is connecting, which is drawing water from this aquifer, which is pretty common. If you have gone to Dhanbad area, which is likely, you can very well anticipate this kind of things taking place. So here you can see this one is being pumped out like this. Is a pump here which is actually drawing water from this. Now it would be our point of interest, right? It would be our point of interest from the time when this contamination taking place till what time it would reach here, because after this time it will continues to be, this water would be polluted, isn't it? Considering that this is what is can be very well be understood here. So here you can see this, that from this one particularly the flow is to be measured. The flow is to be measured. The flow can be measured by means of, say, as I have said, the flow can be measured like K into A into dH by dL. The flow can be measured like this. From this flow we can find out, we can QA is, we can find out, say from this we can find out that in the actual velocity by which this one would be K dH by dL divided by porosity. So you can find out the actual velocity at which this water is moving. So from this, so if you are considering a distance of d, if you are considering a distance, say either you measure this distance from here or this distance from here. If it is at a long distance, if it is a very long distance, so if you find out d here, we can very well find out the time t1 to know that d by v distance, to find out the time, when the water is likely to be polluted, So essentially, if you just take the examples, like say if it is, say the velocity is, for example, if q is equal to say 50 meter per day, and this k is considered to be 0.004, so we can find out that this is, this dH by dl is, so k is q is, this is k, this is k for 50 meter per day, and this is dH by dl is this, so we can find out the velocity, say about, say as you can say 0.2 meter per day. This is number one. Okay, now this v, so we can find out the porosity. If the porosity is given, say 0.02, we find out this porosity, say at about 0.35 or 0.25, whatever, we can find out the velocity as 0.57 meter per day. Now, if it has to travel a distance, say of 1 kilometer, say distance d is 1 kilometer, this is 1000 meter. The time required is, you can see this 1000 meter divided by 0.57 meter per day. So here you can see this would be about say 1754 days, which would be about, say in about 4.8 years, about, say 5 years. So porosity, this is porosity. The velocity of the value of porosity is given. Okay, the velocity, the value of porosity is given. The value of eta is given. So you can see this 5 years. Why I am asking, why I have done this exercise is only to show that the groundwater, the flow is at a very slow speed. It requires, say for 1 kilometer to travel 1 kilometer, it would take 5 years. Okay, it would take 5 years. Naturally, under typical condition, it would take about 5 years to travel in a particular flow condition. But this one is to suggest that though this estimate is very important in the sense, say one can very well say after the mine has started, or after the plant has started, or the toxic waste is being released in the environment, it would take about 5 years to reach a groundwater well, which can have a serious consequence. The serious consequences are many. There are plenty of examples by which the groundwater wells are being contaminated all throughout the world. So even if say 2 or 3 years, maybe this is an important planning decision. This is an important planning parameter. So you have, when you are doing a mining, or whenever you are discharging something into a source which might lead to groundwater, there are many areas where this can be finally be reached to the groundwater. You stand a very great chance that the groundwater would be contaminated.
This problem is very violent, sir.
Very common. Very common. Is a problem. Is a very common and very serious.
No, government has not made any solid rule on this.
No solid rule, and not only that. Even in small calculations like this are quite infrequent in many of the planning estimates. People generally do not use them. So even if so, that is the beauty of this Darcy's law and things like that. Is you can have a very quick first estimate, 5 years, it would take 5 years. So whatever things you want to do, you have to think about the changes within that time, So here, but well, I mean, having said that, this is one is a 5 years and things like that. So here again, as you have said, it has mostly discussed about the flow, but this Darcy's law does not discuss about the dispersion. Let me briefly put light on what is with the dispersion and things like that. So this has there are 3 assumptions to make here. Any case in 1, 2 and 3 assumptions here is that ignore dispersion, I'll just take it out, ignore diffusion,
So if dispersion or diffusion is not so good, then after also 10 to 12 years it will affect.
Yes, it would suddenly, is going to affect suddenly. Ignore dispersion or diffusion of the transported material. Let me explain this. This is ignore dispersion or diffusion. This Darcy's law generally do not take clear care of this. Another is the the polluted substance travels at the same speed that of groundwater, This also is perfectly mixed. When you consider it is perfectly mixed, then you can consider that this polluted substance travels at the same speed as that of the groundwater. And the third is that there is no pumping effect of pumping in between. There is no effect of pumping in between. So in between the 2 holes under consideration, in between the 2 points that we are discussing. So this is the Darcy's laws, the typical assumptions of Darcy's law ingrained with the inefficiency by which the Darcy's law cannot estimate several other things. But let me just briefly discuss about what is the important difference here is that as you can see here, this is, let me point out, this is here, see what is being done here is, if you just observe this Darcy's law, if you make a drawing like this, it goes like as if it is in a plug flow. We call this as a plug flow. What you mean by this is, say this is okay, just 1 minute, let me do that again. As if what we say is just like this. It is, if it is coming out of a pipe, and then it is as if flowing in a very pointed manner. It will have a radius. This is as if a cross section of a pipe. This is how it looks like. This will have a radius r, which is conceptually, r is as small as possible, to idealize that as if the dispersion is taking place, the flow is taking place in a line, in a single line. This particular characteristic is known as the plug flow. This is known as the plug flow. This is one of the consideration of the Darcy's equation. This is one of the consideration of Darcy's equation. But what happens in a natural setting is a natural setting is like this. If you are just if you are making a controlled experiment, this is how it is taking place. Instead of a pointed flow, this is a pointed flow. Pointed flow, or also called plug flow. So you can see this. This is as if the flow is taking place and there is no dispersion. So the concentration of the material being dispersed here would remain the same here as well. The concentration is not getting changed. This is a very simplistic assumption to make. What happens essentially in cases like this is, if you can observe the things like this, is just observe a plot like this. If you are just trying to say, if you are making a column of say sand or anything like this, a material with some permeability, if you are just observing this, if you are just putting this plug flow here, if you are just dispersing this material here, say this is how the material is being dropped in this, what we generally observe is this particular the pollutant is, if it is in the, this is what is through which the water is flowing. So you can have a level of water here, and we are collecting the water at this point here. So what we observe here now is suddenly different. Here in this case, the contaminant, instead of following a single line, then the concentration remaining unchanged throughout the flow direction, throughout the flow distance, the concentration here is likely to change like this. It is going to go out as a plume. This is called a plume. So the plume would be, if you just observe it like this, it would be like a cap. The concentration of the pollutants would be, concentration of the pollutant here would be completely distributed across the cross section of the groundwater regime, across the cross section of the total experimental flow. This is known as, this particularly is known as plume flow. So here, if you remember that one approximation that we made, that here you can very well understand that the contaminant transport velocity, say that you can observe here, say that this is the contaminant getting mixed here, this is the contaminant getting mixed here. The contaminant transport velocity, say VC, contaminant transport velocity, and the groundwater water velocity of the water, this may be quite different, may not be same as velocity of water. It's not necessarily that they have to be constant, because of their the properties being different, the density being different, their other parameters remaining different. So all this can lead to a change in the velocity. So the plume velocity here in the Darcy's case, we have considered at any point of time Vc is equal to Vw. It is not necessarily a case. So in a transformation, generally we call this as, so you understand a plume transport. So you can, here you can see that this is essentially, you can see the concentration is C1 here, say if it is concentration is same here, C2, C3, C4, as you can see, observe here. So it's always C4 less than C3 less than C2 less than C1. Whereas in the other case, in the Gaussian, in the plume, in the Darcy's law equation, we consider that the concentration remains the same across the direction of flow. So this is what, this is the dispersion. This is what is known as the dispersion, and the characteristics of the dispersion would be generally a function. It's a particularly a function which is, say, this transportation, transport. Say if you just can consider here that erase clear all drawings. Here you can see this. If we just make a case like this, the concentration at, say, at a point xc, even in dxcy, this is a function. This would be a function of the initial concentration, say at initial xc0, initial concentration, then aquifer, other parameters like this, aquifer parameters, there's say the hydraulic conductivity, K, porosity at different points, the distance travel, the total distance of travel. So this is xc itself. So here it becomes a differential equation which is much more complex, in considering into a particularly a plume characteristics. We would see this in more detail. We will not discuss about this plume dispersion of this water for this contaminant transport here, but we will have a further discussion on this in our air pollution modeling. We will see that in greater detail about one kind of plume distribution that we generally see, observe, dispersion, plume dispersion that you generally observe. So here you can see this. This is how the concentration across the different aquifers should basically change. If we just observe this, if you just make a case here, one you can see this is okay. So we are basically discussing dispersion. In dispersion, what we are basically we are trying to emphasize here on this, in this dispersion here, that we are generally trying to emphasize is this. So having said this, if you are just making a controlled experiment of this nature, is as I have made the drawing, is a controlled experiment of this nature. We generally can observe, one important attribute here is this. This is the concentration. This concentration, as you can see across, this is time or distance here. This one is in terms of time or distance, or right. This one is or. This one is or. As you can explain in terms of time or distribution distance, we can generally see if it is a Darcy's law coefficient, the way we discuss, this is how the value would be, the concentration remaining constant. But if it is it's a plume flow that we have discussed, the dispersion actually the way it takes place, we can observe that this concentration remaining constant and then finally going to go down like this, with dispersion. This is how the value would be. So this is Darcy's law. This talks about Darcy's law. This is dispersion, plume dispersion. This is about the plume dispersion, that how it would work out like this. Is that clear? What is being done here is, at a particular time, after a certain time, this time may be very short, this is del t, this time is very short. After that we will consider that about the dispersion that I have said, that actually the concentration would be this, the same concentration would be distributed. So here you can see that is the value is actually going down here. So here if you just observe this at different points here, this one is at x1 x2, this one sorry t1 t2, this one is t1, this one is t2, like this. The concentration continuously decreasing as the cross section is increasing, the concentration is likely to decrease. So having said all this, this is how it would be behaving. So as you can see, we would not go into much further distance here, but let us do this flow characteristics. Flow characteristics. If it is a point source, and continuous flow, this is point source and continuous flow. Point source and continuous flow, we generally observe that this is how the plume would essentially behave. This is T1, T2, T3, T4. Point source delivering, where this is the plug flow at one point, point 4 top plug flow at one point, and then in the medium it is getting dispersed. This is how the plume would look like. This is what is the plume would look like. So they're quite similar to what I have said earlier, that it would be like this, further like this. This one can be, if it is overlapped over one another, it would look like this, isn't it? This is a point source and continuous flow. If it is point source and continuous flow, it would look like this. If it is point source with discontinuous flow, the point source with discontinuous flow, it would more look like this. This is a plug flow, this is where it is like this. This is okay. Okay. Okay, let me draw it again. Sometimes it doesn't go. Anyway, let me put this here, right? Here, as you can see, if it is like this would be initially like this. This is starting from here. This is at the point flow. This is the flow direction. This is the flow direction. This is the flow direction. This would begin to expand like this, and then it would be more like this. This is a discontinuous, instantaneous, discontinuous flow. Discontinuous flow at point source. Discontinuous flow at point source. This should be, this is how you can see, this is the time gap, by which there will be no flow. So this is how the discontinuous flow would take place. This would be the plume. This would be the plume look like.
So that means in every plume we can consider Darcy flow also perpendicular to the flow direction.
Perpendicular to the flow direction, yes. This is a plume which says that this is flowing like this. This is flowing like this. Yeah, this is what is dispersion. Darcy's law only discusses about the flow along the head, along the decrease in head. So it is essentially discussing about mostly the transverse flow. But transverse flow, sometimes this longitudinal flow and transverse flow, this longitudinal flow sometimes is more than transverse flow. Transverse flow. So what is observed here is instead of the plume might look like this, the transverse movement has been much more than the longitudinal movement has become much more than the transverse flow. It is quite possible, in most cases it is quite possible that this kind of situation can take place. So in such cases you can see that in that cases it is not quite possible to explain the flow, total flow, by means of Darcy's law. We have to find out another parametric coefficient, parametric functions to deal with this kind of situation. So instead of movement in the x direction, we will have to consider the movement in around y direction. So this kind of thing, this is possible with the differential equations that we will not deal with, but I'll just tell that there is a scope of use of those kind of methods to deal with situations like this. So anyway, nonetheless, this is what is generally it would look like. It is how it would look. It will consider this case. It will be like this. So, but one thing interesting here is you must observe here as that this particular, this one, if you just say this one is x, the direction x, the y1 or y1 here, or both sides, this y2 here, y3, this one is, say, considering that this one is x2, this is x1 here, x2, x3. Always remember x3 is more than x2, more than x1. This is a characteristic of the plume, and also y3 is more than y2 and more than y1. This will always take place. That is why it is taking a shape of a balloon or a plume like this. A balloon continuously getting inflated. This is how the plume would look like in case of a discontinuous flow. Okay. So with this, our coverage on this groundwater flow is complete. We have said, we have seen how this contamination takes place and what are the possible things. Since there are so many things to cover, so we will not be able to discuss about the dispersion in great detail. But this is the basic principle of dispersion. You can see how this mathematical equations can be used to find out the different functional values of dispersion. But we have to stop at this because there are so many other things to cover. After this, we are going to go for wastewater treatment. The next class would be on wastewater treatment. So mid-sem is till this class. Okay, till this class is mid-sem, and that is of post mid-sem we will begin the wastewater management. Right. Okay. Thank you very much.